So, in this fifth lecture of solution, we are going to study colligative properties. What is colligative property? Colligative properties are those property which depends upon the number of molecules present in the solution but not on the nature of the molecule. Whenever we add any particles, then what is the number of particles inside the solution, that will determine the properties of solution. Those properties are called colligative properties. So we can define colligative properties as properties which depends only on number of solute particles but not on the nature. Whether we are adding NaCl or we are adding MgCl2 or we are adding CaCl2, that is not going to affect the properties, colligative properties. Only thing that will affect the properties are whether we are adding one particle, two particle, or when we add it is dissociating to give two particles, three particles, four particles. That will affect the colligative properties. So in class 12th, we have to study following colligative properties. First one is elevation in boiling point. Second one, depression in freezing point, and relative lowering of vapor pressure. And last one, osmosis. Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmosis. So now we are going to study all these properties one by one. So let's suppose P naught equals to vapor pressure of pure solvent. P is vapor pressure of solution. So P naught is vapor pressure of pure solvent and P is vapor pressure of solution. If we talk about the lowering of vapor pressure, means how much vapor pressure is lowered, then that lowering will be in the pure state minus in the solution state, P naught minus P. P naught minus P will be lowering of vapor pressure, and in Raoult's law we have studied that vapor pressure of any component is given as its vapor pressure in pure state multiplied by mole fraction. So the vapor pressure P can be given as P naught into chi1. Chi1 is mole fraction of solvent in solution and P naught is vapor pressure in its pure state. So from here, if we talk about the relative lowering of vapor pressure, then relative lowering of vapor pressure will be P naught minus P divided by P naught. In place of P, we'll write P naught chi1, P naught minus P naught chi1 divided by P naught. So P naught will cancel out and we'll have 1 minus chi1. And we know that sum of mole fraction of solute plus solvent is equal to 1. Whenever we add the mole fraction of all components of solution, that is always equal to 1. So from here we can say 1 minus chi1 will be equal to chi2. So we can write here P naught minus P divided by P naught equals to chi2. This has become the relative lowering of vapor pressure. So we can say that relative lowering of vapor pressure of solvent is equal to mole fraction of solute, and relative lowering of vapor pressure of solute is equal to mole fraction of solvent. So if we prepare solution by mixing volatile solute as well as volatile solvent, in that case relative lowering of vapor pressure of solvent will be equal to mole fraction of solute, and relative lowering of vapor pressure of solute will be equal to mole fraction of solvent. So next colligative property is elevation in boiling point. So if we see elevation in boiling point, first we have to assume that let T1 is boiling point of solvent. When we have pure solvent, nothing is mixed in it, then that solvent has boiling point T1. Suppose if we are taking water and water is pure, nothing is mixed inside the water, in that case whatever boiling point of water is, that will be the boiling point of pure solvent. For example, water has boiling point 100 degrees Celsius, so here T1 will be equal to 100 degrees Celsius. Now in water, if we dissolve some solute, if we are dissolving NaCl or we are dissolving glucose or we are dissolving sugar, whatever solute we add, we may mix some volatile component also. For example, in water when we dissolve ethanol, methanol, propanol, acetone, When we dissolve all these, then the boiling point of solution rises. It has been found experimentally that whenever we add any solute from outside to the pure solvent, then it increases boiling point of solution. This increased amount of boiling point of solution is known as elevation in boiling point. So here if T1 is boiling point of solvent and T2 is boiling point of solution. So with respect to solvent, how much boiling point increased? That will be T2 minus T1, that is boiling point of solution minus boiling point of solvent, because we know that in the solution boiling point will have higher boiling point because we have added some impurity in the solvent, and solvent will have less boiling point because it is pure. So elevation, increase in boiling point will be T2 minus T1, and that will be equal to delta TB. And when we perform experiment, then we come to know that this elevation in boiling point is directly proportional to molality of the solution. What is molality of solution? Molality of solution is number of moles of solute present in 1 kilogram of solvent. So we see that delta TB, elevation in boiling point, is directly proportional to molality of solution. And in mathematics we have studied, whenever we have to remove any proportionality sign, in that case we have to introduce one constant. So for that, delta TB will be equals to Kb into small m, where K boiling point elevation constant or ebullioscopic constant. This Kb is called boiling point elevation constant or ebullioscopic constant, and this small m is molality. Now we will substitute here formula of molality. Formula of molality is number of moles of solute present in 1 kilogram of solvent, and number of moles will be equal to given mass divided by molar mass of solute. W2 is mass of solute and this capital M is molar mass of solute. So when we will divide mass, given mass of solute with molar mass of solute, we will get number of moles, and this W1 is mass of solvent. So mass of solvent in gram. To convert this in kilogram, we need to divide here by 1000. When we will divide here by 1000, it will go upside, so it come here in multiplication factor, that is 1000. So delta TB will be equal to Kb, ebullioscopic constant, mass of solute divided by molar mass of solute multiplied by mass of solvent multiplied by 1000. So this is the elevation in boiling point. From this formula, if we have elevation in boiling point, Kb is known, mass of solute and mass of solvent is known, then we can determine molar mass of solute. So basically the use of colligative property is to determine the molar mass of solute or molecular mass of solute. So with the help of colligative properties, we can determine molar mass. Now next is depression in freezing point. So let's T1 equals to freezing point of solvent. We are going to determine depression in freezing point. So suppose T1 is freezing point of pure solvent and T2 is freezing point of solution. Now the depression in freezing point is different from that of elevation in boiling point. In case of boiling point, when we were adding impurity into the solvent, there was rise in boiling point. But when we add impurity in solvent, then in case of freezing, its freezing point goes down. That's why word is used depression. Depression means going lower. For example, suppose if ice is melting or ice is freezing at 0 degree Celsius temperature, it starts to freeze at 0 degree Celsius temperature. And now if we add some impurity in pure water, suppose NaCl we have added, ethanol we have added, now the same water will freeze below 0 degree Celsius. That may be minus 0.15 degree Celsius, maybe minus 1 degree Celsius, maybe minus 2 degree Celsius, minus 3 degree Celsius, it will be, but will be always lower than 0 degree Celsius. So this decrease in freezing point of pure solvent when it is converted into solution is known as depression in freezing point. So it is similar to that. All the mathematical formulations are same, only the concepts are different. Concepts are, in case of elevation there was rise in boiling point was increasing, but in case of depression in freezing point is decreasing. In the case of boiling, when we were adding impurity into pure solvent, then boiling point was rising. From 100 degrees Celsius, it will become 101, 102, 103, 104, depending upon the amount of solute added. But in case of depression in freezing point, when you add solute into pure solvent, then its boiling point will go down. And that's why this is called depression in freezing point. So mathematically, it has been found that if we have to calculate depression in freezing point, then depression in freezing point will be T1 minus T2. That is freezing point of solvent minus freezing point of solution. You may write freezing point of solution minus freezing point of solvent also, but we know that when we add impurity in the solvent, there is decrease in freezing point. So this difference, if we take T2 minus T1, that difference will be negative. So then you have to write here negative. Freezing point cannot be, we cannot express like that. So to make this delta TF positive, we are writing T2 minus T1. If you write T2 minus T1, in that case you have to write delta TF positive. For example, if you write here T2 minus T1, in that case we will write here negative delta TF, so that we can get this whole value positive. So either of this you can write. So this will be minus delta TF. So here also we have to write minus delta TF. Thus this minus delta TF will be directly proportional to molality of the solution. Already I have told you what is molality. Molality is number of moles of solute present in 1 kilogram of solvent. So delta TF is directly proportional to molality, and from here, if we have to remove this proportionality sign, we have to substitute some constant, and in this specific case, constant is Kf. Kf is known as cryoscopic constant. Name of Kf is cryoscopic. Cryo means at a very low temperature, freezing. So cryoscopic constant. From here, if we put the value and formula of molality, will get delta TF equals to Kf W2, that is mass of solute, divided by molar mass of solute multiplied by mass of solvent, and this whole value will get multiplied by 1000. Molar mass of solute, given mass of solute, divided by molar mass of solute multiplied by mass of solvent, and solvent must be in gram. To convert in kilogram, we'll divide here by 1000. 1000 will go upside, so we'll have Kf W2 by m into W1 into 1000. This is delta TF. From here we can determine again molar mass of solute. So molar mass of solute, again with the help of colligative properties, we are able to calculate molar mass. And in the beginning I told you that purpose of colligative properties is to calculate the molar mass of solute. So from here also we can calculate molar mass of solute. So next is osmosis. What is osmosis? Osmosis is movement of solvent from its region of low concentration. When we say low concentration, this low concentration is in terms of solution. Movement of solvent molecules from its region of low concentration. Movement of solute molecules means, suppose if we have two solution, one solution is of 1 molar concentration, another solution is of 2 molar concentration, and we separate two solution by a semi-permeable membrane, then solvent molecules will move from 1 molar concentration to 2 molar concentration. This process is known as osmosis. So we can define osmosis as movement of solvent molecules from low concentration region to high concentration region is known as osmosis. What is osmotic pressure? Suppose if solvent molecules are moving from its region of low concentration to high concentration, then to stop this movement, we have to apply one pressure from opposite side. The minimum pressure we apply from opposite side to just prevent the movement of solvent molecules through semi-permeable membrane is known as osmotic pressure. So whatever pressure we are applying, same pressure is acting from the solvent side also. When these two pressure becomes equal, there is no movement of molecules of solvent from low concentration region to high concentration region through semi-permeable membrane. and the pressure we are applying to prevent this movement of solvent molecules from opposite side on semi-permeable membrane is known as osmotic pressure. This osmotic pressure is also a colligative properties, and like all other colligative properties, this is also used for determination of molar mass of solute particles. So pi is used for the notation of osmotic pressure. Pi equals to osmotic pressure, and the relationship is osmotic pressure pi equals to CRT, where C is concentration, R is universal gas constant, and T is temperature in Kelvin. We have to write temperature in Kelvin. We'll always express temperature in Kelvin. So T is temperature in Kelvin. Okay, then we know that concentration is defined as number of moles of solute present in 1 liter solution. So from here we can write C equals to N by V, where N is number of moles of solute, V is total volume of solution. So if we substitute this value of C here in this equation, we will get pi equals to N by V RT. And we know N is number of moles, and number of moles equals to given mass upon molar mass, or mass of solute divided by molar mass of solute. So from here we can write pi equals to given mass of solute divided by molar mass of solute multiplied by volume V RT. So this relation gives osmotic pressure, and from this relation again we can calculate molar mass of solute. So here we have seen that in all the three cases, with the help of colligative properties, we can calculate molar mass of solute. So this is graph of elevation in boiling point. So in this graph we can see that this point is the temperature at which pure solvent starts to boil, and this one is the temperature at which solution starts to boil. And on y-axis we have taken vapor pressure, and on x-axis we have taken temperature. So we define boiling point. A constant temperature at which vapor pressure of liquid becomes equal to atmospheric pressure. So when we start to rise temperature, then at T1 temperature, pure solvent acquires vapor pressure equals to atmospheric pressure, and we say that solvent has started to boil. Now if we make the solution by mixing solute into it, then we will get another temperature T2. At this temperature, so vapor pressure of another temperature is T2. At this temperature, vapor pressure of solution becomes equal to atmospheric pressure, and solution starts to boil. So this is final boiling point. This difference is known as elevation in boiling point, and we have established relation between delta TB and molality. This one is graph for depression in freezing point. So if we see depression in freezing point, this is liquid solvent and this one is solution. So freezing point is at this point, we can say, suppose this one T1 is freezing point. This T1 is freezing point of pure solvent, and this T2 is freezing point of solution. So if we calculate the depression in freezing point, this depression in freezing point will be T1 minus T2. So we can write here delta TF equals to T1 minus T2. On the x-axis we have taken temperature in Kelvin, on the y-axis we have taken vapor pressure, and we have already established relationship between delta TF and